Hey, at this point, I'm sure all of you know what LangChain is, but do you want to be one of the first to get your hands deep in on Langgraph? I wanted to really deep dive into what exactly is going on behind this Langgraph and how are they really using graphs in order to really change how you handle LLM executions. So let's get right into it. The first thing I like to do is two things. One, understand all the files, get a good idea of what are the important files, and generate a diagram. So let's first go ahead and look at a diagram. So I'll ask it to draw a diagram of Langgraph. Now here you can see we have each of the main components, which we can take a look into and then better understand how each of the components work and which parts we want to dive further into. So here you can see there's a few main components in Langgraph. First, there is the agent executor. Okay, it looks like that might be responsible for executing the agent, orchestrating the tools, the agent, running the agent, discerning if it should continue. Then there's a chat agent executor. Perhaps that takes in some chat history. There's a pre-built tool executor that handles running tools. And then we have these other classes here. The context, which seems to be a channel. There's a checkpoint, okay, and then the memory saver seems to be seems to be a child class of the base checkpoint saver, as we can see here. It's calling this, so it's a version of that. And then here we can see there's a topic. Again, it's a channel. So it looks like both topics and context are both different types of channels. And it calls the base channel. So there's a few different things that are calling base channel here. You can see there's the topic. There's all the way up here. You can see the context is also of type base channel. The binary operator aggregate. So each of these are of type base channel. So you can try to understand better what a base channel is. And then there seems to be a few other channels. There's the binary operator. Okay. Now that's channels. There seems to be another big class called Langgraph graph state. So there's a state graph. We'll look into how that graph is built. And then there's this whole class called pregel. Now I briefly skimmed the Langgraph documentation, and it looks like pregel is this actual graph library that Langgraph is working with. So we can look deeper into how pregel works and what it's doing. So it looks like pregel read has two main functions, channel batch and channel invoke. And those call channel read, which has a few async functions. Then there's channels.lastValue, channel write, and channel read. Okay, great. So now that we have this overview of what the whole Langgraph library looks like, we can break down each of these different components to understand better the state graph, the agent executor, channels, the differences between topics and context, and then how the pregel graph works with the read, the write, and how it works with channels and the agent executor and all of that. So now that we have this idea of what we're looking at, let's really dive deep into each of these different components. So as we can see, here's a high-level file path of the directory. And you can see that there's examples. This walks us through the main examples we can take a look at. There's channels. So now channels, as we saw, there's a few main channels. There seems to be a topic, a context channel, a base, and a binary operator aggregate. All right. So we can look into these in more detail. It looks like the context channel defines a class called context that exposes the value of a context manager for the duration of an invocation, provides functionality for entering and exiting the context manager, as well as retrieving the stored value. The topic represents a configurable pub subtopic. It has functionality for updating the topic with values, getting the current values, and creating a checkpoint of the topic state. A checkpoint is, okay, so memory seems to be is a type of checkpoint. So this file defines a class called memory saver that extends base checkpoint saver and provides functionality for storing and retrieving checkpoints in a dictionary. All right, so that's kind of how the channels and the checkpoints and the memory work. We can dive deeper into those in a minute. Then you have the graph, which contains the implementation of the Priegel algorithm, which is a parallel graph processing model, and it includes functionality for subscribing to channels, writing to channels, and executing the Priegel algorithm in both synchronous and asynchronous modes. All right, so let's really dive deeper into what Priegel is doing as well. Okay, so now let's just go into each of these different components. So I'll ask it first to explain the Priegel algorithm in detail. How does it perform parallel graph processing? Right, so the Priegel algorithm is a parallel graph processing algorithm that allows for efficient computation. It operates in a series of super steps where each super step consists of 3 phases: computation, message sending, and message receiving. During the computation phase, each node applies a user-defined function to update its state based on the current state and the messages received in the previous super step. The updated state is then sent as messages to its neighboring nodes during the message sending phase. In the message receiving phase, each node receives messages from its neighbors and stores them for the next super step. All right, so here we can see kind of an implementation of this. It's implemented using nodes and channels, so each node can receive and send messages. And channels represent the communication channels between nodes and facilitate the exchange of messages. So here you can see it's creating a Priegel application with a node and a channel, and it has this input and output channel. And then you create a graph, add the node, set an entry point and a finish point, and then you compile the graph. Then you can invoke it. In this example, the Priegel application consists of a single node and input and output value. Okay, so from now, let's try to decompose the role of nodes and channels in the implementation of the Priegel algorithm. The nodes represent the computation units or processing units. Each node performs a specific computation, and channels allow nodes to send and receive data or messages from the other nodes. The Langgraph library handles data transformations between nodes using each of these components, right? So there's the channel, which passes data, a topic, and context. So topic allows data to be published to a specific topic and subscribed to by other nodes. And you can have multiple nodes listening to the same topic. Last value is a channel stores the last value received and passes it to the next node. And context, this channel allows the sharing of context data between nodes. The Priegel read and write stages, how are they different and what does each stage do specifically? So the read stage is responsible for reading the data from input channels. And then the write stage is responsible for writing data to output channels. It takes the output of the computation and writes it to the specified output channel. And it's often used to store the results of computation or pass data to the next stage of the computation graph. So here we can look at some actual pseudocode of how this works, right? So as you can see, you can have each of these nodes. You have 2 nodes, 1 and 2, and then it subscribes to input and it writes to output. And again, you have another 2 subscribes to input, writes to output. And then here you essentially create a Priegel app with that graph. All right, so now you can see this is the state graph. The state graph is the representation of the graph. So it has a node, an add and edge, set entry point, finish point, and compile. So this is what this graph representation ultimately has. And you can run set graph. Yeah, so once you create a graph, you can add each of these. And then you call app.invoke. And yeah, it takes in what you asked for. Now what now let's look more into what exactly the memory saver is doing, topics, channels, how they're different from each other. So a memory saver class is a subclass of the base checkpoint saver, and it's defined essentially using this config specs, and it stores the representation at a given point in time so that you can checkpoint your agent's execution. The Pregel framework utilizes the memory and memory saver classes for saving and retrieving checkpoints during the execution of the Pregel computation. It is responsible for storing and retrieving checkpoints during the execution. And here's an example, right? So you define the memory and then you have a saver, and that takes this memory. In this example, the memory class is instantiated and passed the saver argument to the Pregel constructor. This allows the Pregel framework to save and retrieve checkpoints using the memory class. The memory saver class is a subclass of base checkpoint saver and provides an implementation for saving and retrieving checkpoints using an in-memory storage mechanism. Great, so now let's try to understand better how this memory saver, topics, and channels, how are they all related, right? So we understood that memory saver is a checkpointing mechanism. Topics are channels that allow multiple subscribers to receive updates from a single publisher. And channels are communication channels between nodes in a graph. And they can be used to subscribe to topics, perform operations on data, and write data to other channels. So we can have, channels can have different types, such as topic channels for publishing and subscribing to topics, and context channels for passing context information, and last value channels for storing and retrieving the last value written to the channel. So here you can see pseudocode for a topic. It allows you to update, get, and checkpoint. Yeah, and if you want to write and read from a channel, you can do channel.write_to, channel.subscribe_to. There's a few key differences between topics and context. They're different value and update types. Topic channels accumulate updates, context channels do not accumulate. Topic channels can be set to enforce uniqueness, so there's no duplicate values, while context channels do not have that feature. Checkpointing, topic channels can be checkpointed, context channels cannot. Topic channels can be used as input or output in a Pregel computation, but context channels are only used as input. Great, now there's a lot more you can continue to ask to understand, the diagram of the chat agent executor, how is the agent state represented, and then we can also look into each of these examples. How is the draft revise loop set up? It's set up using the Pregel class from the Langgraph library as a drafter, editor, reviser. Each of these different chains determines what's the input, the output, and how the channel handles writing it. Okay, great. Hope you have a good understanding of Langgraph.